Okay, for infinity times 0. So these other forms from here until the end, you have to do a little bit of algebraic trickery to convert it to a form where L'Hopital's rule will work. So for this example, we'll look at the limit, excuse me, as x approaches pi over 2 from the left of pi over 2 minus x times tangent x. So first, we will check our form. As x approaches pi over 2 from the left, pi over 2 minus x approaches 0, and the tangent of x approaches positive infinity. Just picture the graph of y equals tangent x. This is where you're approaching a vertical asymptote from the left side. Okay, now the thing that's tricky about this particular form is that sometimes it's difficult to decide. So we have here an f times g, right? A function times another function. So sometimes it's difficult to decide, okay, should I change this f times g into f divided by 1 over g or g divided by 1 over f? And the rule of thumb is that you should make the choice that's going to give you simpler derivatives. All right, so in this case, and I can't swear that this is going to be the right choice. Sometimes, even after all the years I've been doing this, I still don't choose correctly, and that's fine. I just start over when I don't choose correctly. But in this case, I think I'm going to do pi over 2 minus x divided by cotangent of x. And the reason I think that's going to work is because pi over 2 minus x has a very simple derivative. And I also know the derivative of cotangent x. If I had done it the other way, it would have been tangent x divided by 1 over pi over 2 minus x. 1 over pi over 2 minus x has a sort of complicated, messy derivative. Okay, so checking the form again, notice I don't have the little L apostrophe H over here because I was not using L'Hopital's rule. I was just rewriting it. Pi over 2 minus x is approaching 0, and the cotangent of pi over 2 is 0. So now this is in the form where I can use L'Hopital's rule. So let's use it. The derivative of pi over 2 minus x is -1, and the derivative of cotangent x is negative cosecant squared x. And as we've used twice before in this same section, the cosecant of pi over 2 is 1. So this limit is equal to 1. All right. Next, I believe we're going to look at infinity minus infinity. So this is another interesting one. Imagine a really big number minus a really big number. Well, I have no idea what that could be. I mean, if it's a trillion minus a million, that's still a really big number. If it's a trillion minus a trillion, well, that's 0, right? So infinity over minus infinity, sorry, gives me no information about what the value of the limit might be. And so the trick that usually works with this is to combine it into a single expression, which is what I'm going to do in this problem. All right, so switching back to the tablet. We have the limit as x approaches 0 from the right, 3x plus 1 over x minus 1 over sine x. Checking the form, as x approaches 0 from the right, 3x plus 1 approaches 1. And x is a teeny tiny itty bitty positive number, which means that first expression is going towards positive infinity. And as x approaches 0 from the right, sine x also approaches 0 from the right. So in that second term, you're looking at 1 divided by an itty bitty teeny tiny positive number that's also going toward positive infinity. So combining this into a single expression, whoops. All right, I need a common denominator, which is going to be x sine x. So I am going to multiply the top and the bottom of this expression by sine x. I'm going to multiply the top and the bottom of this expression by x. And that is going to give me 3x plus 1 sine x minus x over x sine x. So I think this one's going to be a little messy. All right. But let's see what we can do with this. Okay. Just trying to think ahead a little bit, because I have a feeling if we try applying L'Hopital's rule on this right away, it's going to turn into a big mess. Let's verify that this is the right kind of form. So if you plug in 0, you have 1 times 0 minus 0. So that's definitely 0. And on the bottom, you have 0 times 0. So this is a 0 over 0. But before I use L'Hopital's rule, I am going to play around with this a little bit. If we distribute that sine x, this one right here, we have 3x sine x plus sine x minus x. And on the bottom, we have x sine x. So I have a feeling that it might be a good idea to break this into 3 separate terms and see what that does. Okay, so if we break that into 3 separate terms, each with denominator x sine x, then the first term is just going to be 3. The second term is going to be 1 over x. And the third term is going to be x over x sine x, which is 1 over sine x. Okay. All right, so now what we have is plugging in 0 or imagining 0, approaching x approaching 0 from the right. We have 3 plus infinity minus infinity. So this is still infinity over infinity, but you know what? Let's get rid of some of this stuff on top. It at least won't be quite as messy as if we had kept it the way it was. Because, for example, we can just take that 3, and we know the limit as x approaches 0 of 3 is just 3. So we'll think of this as 3 plus the limit as x approaches 0 from the right of 1 over x minus 1 over sine x. Okay, and now I am going to combine those two into a single fraction. And I think that that'll be nicer than what we had before. Okay, so doing the same thing I did before with common denominator, this would become sine x minus x over x sine x. Okay. And now I think I'm ready to use L'Hopital's rule, because this does have the form 0 over 0. I have a feeling that if I had just been just a little bit more clever about the way I had broken up this expression here, I probably could have saved a step or two, but Yeah, that's life. All right. So using L'Hopital's rule, don't forget about this 3. We'll just keep that there. The derivative of sine x minus x is cosine x minus 1. And then the derivative of x sine x by the product rule is the first times the derivative of the second plus the second times the derivative of the first. And this, unfortunately, is another 0 over 0. Okay, so we'll use L'Hopital's rule again. Here, can I do this? Ditto, ditto, right? I like to call it old school copy and paste, the ditto marks. Okay, so one more time. The derivative of cosine x minus 1 is negative sine x. Okay, now the derivative of x cosine x by the product rule is x times negative sine x plus cosine x. And then the derivative of sine x is cosine x. And now I think we're in business. Because if you substitute 0 into that, you get 0 on top. Well, let me just show you. 0 on top. X sine x is 0. Cosine of 0 is 1. Cosine 0 is still 1. That is a 0 over 2. That is not indeterminate. That equals 0. So this whole entire limit is equal to 3. Wasn't that fun? All right, back to the presentation. One more thing to show you. Indeterminate powers, such as 1 to the infinity, 0 to the 0, or infinity to the 0. It's a little bit harder to explain why these are indeterminate, but those are the 3 that are indeterminate. So it turns out the trick with these is to use logarithms. All right, and I'm going to show you how I do it. Here are the 2 examples. The way that I write it up is a little bit different from what I've seen in some books. I like to think that my way is maybe a little easier to follow. Okay, so here we go. Starting with the limit as x approaches 0 of x to the power 1 over natural log x. So first checking the form. The form of this one is infinity to the power 1 over natural log infinity. As x approaches infinity, natural log x also approaches infinity, which means 1 over natural log x approaches 0. So this is one of those indeterminate forms. So here's how I like to do this. That gives me no information about the value of the limit. I have no idea what this limit is, so I'm going to call it L for limit. Let L equal the limit as x approaches infinity of x to the power 1 over natural log x. And then what I'm going to do is I'm going to take the natural log of both sides. Therefore, the natural log of L is equal to the natural log of limit as x approaches infinity, x to the power 1 over natural log x. Natural log is a continuous function. And back in Calc 1, you learned that a property of continuous functions is that they can be pushed inside of limits. In other words, the natural log of the limit is equal to the limit of the natural log. And maybe at this point, you can kind of start to see why I'm doing this. Now that that natural log is next to the power, I can use my favorite property of logarithms and say, okay, and also, by the way, I really should write natural log L at every step, and you'll see why in just a second. Okay, so that means that the natural log of L is equal to the limit as x approaches infinity, 1 over natural log x times natural log x. Oh, look at that. Those natural log x's cancel. And I don't, oh wow, we don't even need L'Hopital's rule in this problem because I think you know that that limit is equal to 1. Now, looking this over, do we have our answer? Well, no, we don't. The answer is L. We have natural log of L, all right? So at the very end, you just have to remember to exponentiate now both sides of that equation. E to the natural log L is equal to E to the 1. So believe it or not, this limit is equal to E. This limit is equal to E. All right, and now for the last example. The limit as x approaches infinity of 1 plus 1 over x squared to the power x. Checking the form of this one. As x approaches infinity, 1 plus 1 over x squared approaches 1. And of course, x approaches infinity. This was another one of our indeterminate forms. So let's call that answer L. And take the natural log of both sides. So we have natural log of L is equal to natural log of limit x approaches infinity, 1 plus 1 over x squared to the power x. Pushing that natural log inside the limit. We have limit as x approaches infinity of natural log 1 plus 1 over x squared to the power x. Using my favorite property of natural logs, we can take that x and go, and we have natural log of L is equal to the limit as x approaches infinity of x times natural log 1 plus 1 over x squared. Okay, so at a certain point, you recheck your form. As x approaches infinity, well, x approaches infinity, right? And 1 over 1 plus 1 plus 1 over x squared approaches 1, and the natural log of 1 is 0. So now this has the form infinity times 0. And what did we say about that form? We said that instead of multiplying those two things together, you divide one of them by the reciprocal of the other, all right? So in this case, I think what we're going to do is, let me just recopy this real quick. Natural log of L is equal to the limit as x approaches infinity, x times natural log 1 plus 1 over x squared. Okay, so I think what we want to do here is rewrite this as natural log 1 plus 1 over x squared over 1 over x. So instead of multiplying by x, we're dividing by 1 over x. And now this thing has the form 0 over 0. So now finally we can use L'Hopital's rule. Oh dear, I hope this all fits. Okay. The derivative of natural log 1 plus 1 over x squared would be 1 over 1 plus 1 over x squared times the derivative of 1 plus 1 over x squared. And that derivative is negative 2 over x cubed. And I'm going to let you convince yourself of that. The derivative of 1 over x is negative 1 over x squared. So I think what we want to do with this is just try to clean it up. Okay. So let's see if we let's just multiply the top and the bottom by x cubed. You know what? Let's make it negative x cubed, and then we can knock out those negative signs. That's going to give us 2 over 1 plus 1 over x squared divided by x. All right. So again, I probably could have been more clever about that. I think I'll just finish this up here. Okay, because I still want to pretty this up a little bit. It's still a complex fraction. So let's see. Why don't we just multiply the top and the bottom by 1 over x? No, why would I do that? Hold on. Let's multiply. Whoa, darn it. Hit the undo button too many times. My goodness. Okay. Let's multiply the top and the bottom by x squared. And then it won't be a complex fraction anymore. So that's going to make it, you know what, let's put our natural log L back in here. I don't want to forget that that's what this is. Limit as x approaches infinity. Let's see now. Oh goodness, is that what I wanted to do? Okay, I had to pause for a second there and not only get something to drink, but also collect my thoughts. I think I'm starting to get tired here. We want to multiply by 1 plus 1 over x squared. We want to get rid of this stuff. There's probably a simpler way to do this, and I'm just not seeing it. Sorry about the coughing. Okay, so that's going to give us 2 over x times 1 plus 1 over x squared. And at this point, I think we can just evaluate this limit. We don't have to pretty this up forever, because as x gets bigger and bigger and bigger, this thing goes towards infinity. This thing here goes towards 1. So you have 2 over a really, really, really big number. That's going to get closer and closer to 0. All right. So finally, since the natural log of L is equal to 0, That means that e to the natural log L equals e to the 0, which means that L, the limit that we're looking for, is 1. All right, and there you have it. That's going to finally take care of 7.5, and we'll see you next time.